Hi everyone. So in this video we have just finished up making a claim about the first fundamental theorem, the first part of the first fundamental theorem of calculus. I don't even know what I'm saying anymore. And what I want to do now is just practice with what that says. Okay, so what it says, I've got it written right up here, is that if you want to find the value of the definite integral of function little f, you need to first find its antiderivative big F and then plug in B and A, excuse my yawning, and subtract. So down here, I'm trying to integrate the function sine x, which means I first need to find the antiderivative of sine x. So I'm asking myself, what do I take the derivative of if I want to get sine x? And I immediately jump to cosine x, but I have to be a little careful because the derivative of cosine is actually the opposite of sine. So if I don't want that extra minus in the mix, I need to throw one in that cancels it out. And then there's a handy little bit of notation you can use to show that you need to plug in both of these values. That vertical bar is like evaluate at, so you can actually write that down and specifically show top and bottom values, and it'll mean exactly what we want. It'll mean plug in the top value and then plug in the bottom value and subtract. If you think there's any room for confusion, you're welcome to put an x equals on that. If there's only one variable, you don't have to. So I'm going to say, okay, I'm going to get negative cosine of pi over 4. And I'm going to get negative cosine of 0, but since I'm supposed to subtract that second one, it's actually going to end up being a plus. So I get, let's see, pi over 4 is right smack in the middle of quadrant 1, so both cosine and sine, both x and y, are going to be 1 over root 2. So I get a negative 1 over root 2. You can also use root 2 over 2 if you like it. I don't care. I don't require to rationalize denominators, but if that's how you've got it in your head, use it. And then cosine of 0, so that's our x value over here when our angle is 0, which is 1. And I want you to realize that what we've just discovered is that if we look at this graph of y equals sine x, and we go to 0 to pi over 4 and accumulate and count up all that area, that what we will get is 1 minus 1 over the square root of 2, or 1 minus root 2 over 2. So we can now find by hand exact answers to the area question we've been working on. Okay, one more thing I think I want to point out. So this represents area under little f, right? This is still our original function, y equals sine x. This represents the change in y for the antiderivative. Erasing as I write. Change in y. So remember, when you plug b into the antiderivative, you're going to get a y value of the antiderivative. When you plug a in, you get a different y value. When you subtract, you get the difference between your y values, or the change in y for big F. So we'll just say change in big F. How about that? Okay, second one. I put this in here deliberately so that I wouldn't forget to make another connection. So really what the first fundamental theorem is all about is making this connection between derivatives and antiderivatives and antiderivatives and integrals. So we want to tie all that back together. So the definite integral thing, we've just made a claim that there's a big connection between definite integrals and antiderivatives. And I want to make that claim, or that idea, even a little bit stronger and easier to remember by saying to find a definite integral, we find the antiderivative and evaluate at limits. If we're just finding an antiderivative in general, we don't have any limits of integration or anything like that, we can still call it an integral. It's just called an indefinite integral. So let's see, I'm going to zoom in because I know it won't fit. And I think I'm being a little rambly about this, but the point that I actually want to make here is that antiderivatives have another name that kind of helps make this connection. An antiderivative can also be called an indefinite integral. Those are exactly the same thing. And this notation right here implies that I'm trying to find an indefinite integral. So when you see the script S and you don't have any limits of integration, that's just saying find the indefinite integral or antiderivative. And I gave you a little bit of a tricky one so we could remember this. Not super tricky, but a little bit. I am now asking myself, what is the antiderivative of e to the w over 2? Or in other words, who do I take the derivative of to get e to the w over 2? And if you know your exponential functions, you know that they tend to be their own derivative or really close to it. So I'm just going to guess an e to the w over 2. When I check myself, let's see if I have a good check color. The derivative of e to the w over 2, so this is the check, is e to the w over 2. That's great, but there's a chain rule. The chain rule says you also have to multiply by the derivative of the inner part, which is the exponent. The derivative of w over 2 is 1/2. Think w over 2 is 1/2 w, so the derivative of 1/2 w is 1/2. And this is not quite right because I don't want a 1/2 to end up out in front, so I'm going to throw in an extra 2, which would then cancel it out. So now I have a 2 e to the w. And you can see that the 1/2 and the 2 cancel, and I get exactly what I want. So I'm pretty close. One last thing I need to remember, an antiderivative, the antiderivative, so indefinite integral is the antiderivative, not just one of them, needs a plus c. And that actually reminds me of another point that I should make up above. And being a little not careful about things today because I know them in my head and I'm not thinking about what's in your head, is here when I went antiderivative of sine is opposite of cosine x, that was an antiderivative, not the antiderivative, but that's completely acceptable when you're using the first fundamental theorem. Think about if I had put a plus c in here, then when I plug in pi over 4, I'd get opposite of cosine pi over 4 plus c minus opposite of cosine 0 plus c. And when I distribute this minus in, this would become a minus c, not a plus c. So I would have negative 1 over root 2 plus c plus 1 minus c, and the c's would drop out. So when you're doing definite integrals, you just pick any antiderivative. Usually we pick the one that has c equal to 0, so we don't have to think about it. When you're doing an indefinite integral, that's asking you for the antiderivative. This is an antiderivative. Okay. Let's move on to the next one. At any point now, you've got a couple of examples. Please pause and try and figure out some of these on your own, and then you can come back and check if you get stuck. So we're back to a definite integral for this third one. Finding an antiderivative is slightly tricky, but not terribly tricky, just to remind you. If you get messy fractions like this, you'll want to split them up. We want to get back to one of our basic power functions or trig functions or something of the sort. So if I do a 2y over y squared minus a 3y to the 4th over y squared, that's the kind of breaking up I want. And that leaves me with 2 over y minus 3y squared dy, and from 1 to 2. Okay. And I can even go a little further. I'm going to think about that as 2 times 1 over y. So this is actually one that tricks people even aside from the splitting it up. Remember that the antiderivative of 1 over y does not involve a reverse power rule. We'll see if I can make it through any videos without yawning at you today. 1 over y is the derivative of natural log. So what I'm getting here is the 2 just hangs out, comes along for the ride. The antiderivative of 1 over y is the natural log of the absolute value of y. And again, on that absolute value of y, all we're trying to do is make sure that the antiderivative and the function have the same domain, the same way we would want that to be true if we were finding a derivative. So since 1 over y can take anything but 0, we want its antiderivative to do that as well. And we don't just get to decide in general that we can throw an absolute value in, but it does work here just because of the symmetry that we have on 1 over y. It turns out that both parts of that 1 over y graph have natural log as their antiderivative. Okay, and then the antiderivative of negative 3y squared is just going to be negative y cubed. And then I want to kind of use my evaluate notation. I'm going to use it a little differently. I'm going to actually bracket it off so that it's clear that I need to evaluate the natural log as well as the y cubed. So, all said and done, I get 2 times the natural log of 2. You can write in the absolute values, but they're completely unnecessary at this point because 2 is positive. Minus 2 cubed, which is 8. And that's the minus that was already built in here, not the f of b minus f of a minus. Here's the f of b minus f of a minus. When I plug in 1, the natural log of 1 is 0. I absolutely expect you to know that. I'm going to be really grumpy if you ever write the natural log of 1 down and don't simplify. Remember, natural log is base e, so I'm asking what power of e gives me 1, and the answer is definitely 0. E to the 0 is 1. So I get 2 times 0, that's completely gone. But then I have a minus 1 cubed, which is just a minus 1. So when I put it all together, 2 times the natural log of 2 minus 8 plus 1 is minus 7. And again, on definite integrals, you just pick any old antiderivative you want. So it's deliberate that I'm not putting a plus c on those. Whereas for indefinite integrals or antiderivatives, you need that plus c. Okay. Next one. Again, I'm just trying to throw out some of these messier ones for you again. So integral from 0 to 1/2. I'm going to rewrite just a tiny bit. You don't even need to rewrite this one, but I just want to make sure you all see it. This is one that people will get stumped on and they will stare at it, and it's really just one of our basic functions showing up. So you just have to remember that 1 over the square root of 1 minus t squared is the derivative of arc sine. So the 1/2 is just going to carry through. We need an arc sine t so that we get that derivative of 1 over the square root of 1 minus t squared. And then we're going to evaluate from 0 to 1/2. And again, you can always check the derivative. So we're going to say we have 1/2 arc sine of 1/2 minus 1/2 arc sine, or inverse sine if you prefer, of 0. And again, you get to decide whether what your plus c is for a definite integral, so I just generally choose plus c to be 0. And then if we're thinking about arc sine is saying what arc length will make sine, or y, equal to, and so the first one is y equals 1/2, which is toward the bottom of quadrant 1. Arc sine's always going to put us over in quadrant 1 or quadrant 4. This is our pi over 6. So always going to give you that first angle that gives you y value 1/2. So I have a 1/2 of pi over 6 minus arc sine of 0, which is actually 0, so I don't even need a minus. What arc length makes your y value 0? The first answer is going to be arc length 0 makes y 0. There are other answers, but arc sine won't give them to you. So my final answer here is a pi over 12, which means if you look at the graph of 1 over 2 times the square root of 1 minus t squared, and you try and calculate the area trapped under that thing between 0 and 1/2, you're going to get pi over 12. Okay, next one is back to the indefinite integrals. So no limits of integration. This is just saying find the antiderivative. This one, once again, needs a little bit of work. So I would say first thing, I want to actually FOIL out v squared plus 2 times itself. So the v is just going to hang out in front, but I'll have a v to the fourth plus 2v squared and another 2v squared, so 4v squareds, and then plus 4, which is v to the fifth plus 4v to the third plus 4v. And the antiderivative will just involve reversing the power rule. So we're going to want to bump up to v to the sixth and then divide by that 6. For v cubed, we're going to bump up to v to the fourth, which means when we divide by 4, it'll just cancel that. And then for v, we're going to bump up to v squared, and we're going to divide that 4 by 2. So there's my answer. As always, really good plan to take a quick derivative to check yourself. That not only checks for you, but also I think will help you understand why what you've got doesn't work. So really, really good thing to practice. Okay, last one, definite integral from 1 to 2. Am I really boring? Or are these all 1 to? Nope, I guess only one of them. Of this mess. Okay, second question. Yeah, I'm really boring. Okay, I don't know why this one is showing up here twice, but we will just not worry about it. I think that should be giving you a pretty good idea of how to calculate both definite and indefinite integrals. So definite integral is the area under your curve. To find it, find an antiderivative, plug in the limits of integration, and subtract. Indefinite integral is just an antiderivative. Don't forget plus c on those. Thanks for watching.